example, we'll be looking at sizing a pump. This is kind of a classic pump sizing type of exercise that as an engineer, you're expected to know how to do. And what we're talking about in this example is we have a reservoir at an elevation of 150 meters, and we're going to pump, in this case it's going to be oil, through 300 meters of 200 millimeter diameter pipe, which is roughly 8-inch pipe. The pipe has a friction factor of 0.003, so we'll be using that friction factor when we figure out the friction losses. And we're pumping it from the reservoir at 150 meter elevation to an elevation of 200 meters, okay? And at this point here, this is where it's going to discharge from the pipe and go into another reservoir, okay? We're given the flow rate that's required of 0.244 meters cubed per second. Again, as I mentioned, we know that it's an oil. It's got a specific gravity of 0.87, so it's roughly 87% the weight of water. We're given a pump efficiency of 78%, and in this problem, we're going to be ignoring the minor losses. Essentially, what we're assuming is that with the length of the pipe and the large flow that we have, our friction losses are going to govern. So the minor losses from bends, going in and out of valves, and things like that are going to be really minor. That, and we really just don't have that much information about the problem. We don't know how many elbows there are and what type of elbows they are and so forth, okay? So let's go ahead and get started. Looking at this problem, again, when I see that there's going to be head losses, I know that I'm going to need a velocity term going through here, so I'm going to go ahead and solve for that. Looking at the continuity equation, conservation of mass, okay, we know that flow is equal to the velocity times the area. So in this particular case, the velocity going through the pipe is going to be whatever the flow is over the area, okay? Our flow is given as 2.44 cubic meters. Let me correct that here. Cubic meters per second. And then our area is pi over 4. And then we have a 200 millimeter diameter pipe, which is 0.2 meters. And we'll square that, okay? And when we solve for that, it gives us a velocity of 7.77 meters per second. Okay, we need that, so I'll go ahead and underline that. Okay. Now let's get to the engineering side on this. So what we're going to do is we're going to write the energy equation from 2 different points. So I'm going to pick, and again, you can pick any 2 points you want, but why not pick points that make the problem easier? And for me, those are points where I know things. For example, I know the elevation here at the water surface, so I'm going to use that as my first point. Okay, and I also know the elevation at the point where the oil discharges from the pipe, which is 0.2 here. Okay, so I'm going to start by writing the Bernoulli equation between those 2 points. So the Bernoulli equation, 0.1 to 2. I'm going to write the generic version of it. Let me get another marker here. It's a little darker. Okay, we'll do Z1. We're going to add the pump head, which we talked about in the lesson. And then at 0.2, I have the pressure head plus the velocity head plus the elevation head. And then we have to consider the losses due to friction. Okay. So again, this is just a general expression. Now let's start looking at the individual terms. Okay. I know that both P1 and P2 are going to be atmospheric pressure, okay? Because again, 0.1 is at the water surface, 0.2 is just outside the pipe after the water has exited the pipe, okay? So that eliminates these 2 terms here, okay? The velocity at 0.1 is going to be 0. If you think about it, say for example, if you went down to Lake Ruby, or if you looked at just the water in a swimming pool, at the water surface, the velocity is really, really small, if any. And then if you square that small velocity and divide by 2g, it's definitely going to be really small. So we're just going to ignore the velocity because it's so small. We're going to assume that's 0. Okay? We can't do the same thing at 0.2 because at 0.2, that's where the water's exiting the pipe. It's definitely not going to be 0. All right. Now, when I look at the equation, I have Z1. Okay, Z1 represents the elevation at 0.1. That's the 150. So we have 150 plus the pump head on the left-hand side. That has to equal the velocity head, the V2 squared over 2g, okay, plus Z2, which we know is 200 meters, okay, plus, and then we're going to look at the head loss due to friction. We're going to go ahead and use the Darcy-Weisbach equation that we've been using most of the semester, which states that the head loss due to friction is the friction factor, the length of the pipe over the diameter of the pipe, and then we have that velocity head, that V2 squared over 2G. Okay, so looking at this equation, now you see why I solved for the velocity earlier, okay? The velocity that I solved for is the velocity at point 2. It's the same velocity throughout the pipe because the pipe is 200 millimeter diameter pipe throughout. So now all I have to do is just substitute into those terms. So I've got 150 plus EP is equal to, I've got 7.77 squared over 2G. Actually, well, that's fine. I'll just keep the G that way. I've got 200, and then my friction factor is 0.003. The length of the pipe is 300 meters. All right, the diameter of the pipe is 0.02. We just have to make sure, that's the most common mistake, by the way, is that people sometimes put in the 200 millimeter term right here. You have to make sure if you have meters in the numerator, you have meters in the denominator, right? We're working in constant units here. And then 7.7 squared divided by 2G. Okay. Now our G, of course, is going to be, in metric, it's going to be 9.81. So when I solve for this, I get that my pump head comes out to be 66. Let's see. Actually, if I can erase that, let's just make that a little clearer here. Sorry, sometimes I get a little sloppy on my sixes. 0.92 meters. Okay? Okay. So what that's telling us is this. Remember, the pump head is more than just the elevation change, right? The elevation change is going from 150 to 200 meters. There's 50 meters of elevation that the pump has to overcome, right? It has to pump up 50 meters in elevation. But there's also another 16.9 meters of friction losses that the pump has to overcome as well. Now, this is great. We've got the pump head, but what we're actually looking for in this problem is to size the pump. So we have one more step with this. Now, if we look at the power equation, and if you ever get to the point where you just forget what the equation is, you can reason this out. Okay. In the numerator, we have to think to ourselves, it matters what we're pumping. It matters, for example, if this was oil. It matters if it was water. Whatever it might be matters in terms of the weight of the fluid. So we have to consider the specific weight. Okay. What else matters is the flow, right? In terms of sizing a pump, if I tell you, well, you need a pump that's 10 gallons per minute or 1 gallon per minute, it matters what the flow rate is. Okay. Of course, we have this pump term, the pump head, right, which is a combination of the elevation difference and all the losses that the pump has to overcome. And then we divide that by the efficiency of the pump itself. Okay. When we divide by the efficiency, in our case is 78%. By dividing by 0.78, basically we're bumping up the size of the pump. We're saying, look, the pump's not going to work at 100%. So we actually have to increase the size of the pump to overcome the fact that it's only 78% efficient. So let's go ahead and substitute the terms in here. So we've got oil, which has a specific weight of 0.87 times that of water. Okay, we're dealing with metric, so that would be 9810. Again, those are newtons per meter cubed. Okay, our flow rate was given to us at 244 meters cubed per second. And then, of course, we just solved for that pump head at 66.92. Okay, and we're going to divide that by 0.78, which is the efficiency of the pump. When we do that, we get 178,675.9 Newton meters per second. Okay? You're probably thinking at this time, wow, that's a really large number. I've never heard of sizing a pump for 178,676 roughly Newton meters per second. What we have to realize is this term right here is actually a watt. Okay, that's an energy term in watt. So usually on the metric side, when we size pumps, we size them based on kilowatts. Okay, so what we're saying is if we have 178,675.9 watts, in 1,000, you have 1,000 watts to a kilowatt, okay, the pump size would have to be about 178.7 kilowatt pump, okay? So technically that's the answer. Now, in terms of choosing a pump, you can't go to a pump manufacturer and say, okay, we want a 178.7 kilowatt pump. You know, we'd have to probably either go with, depending on the specific brand and its characteristics, either maybe a 175 or perhaps say the next size up, which is 200 kilowatt pump, okay? So at this stage in the game, we've sized the pump. We know more or less what we're going to need. It would be now talking to the pump manufacturer, looking at specific models to determine if it has to be the 175 or we need the 200. And that concludes this example of a pump sizing exercise.